related to bending stress for different type of cross sections. Always remember, we are going for all symmetric members. I'm not taking any asymmetric or multi sections or multi different materials, right? Like composites, being made up of wood and concrete or wood and steel and wood and so on. I'm not going for combination. I will do only for simple metals. If it is metal, throughout metal. Let's start with simple calculations of single element and then go for composite in the higher classes. Now start with number one is the beam given to you, cantilever beam. Can you all see the screen? Let me check the screen first. It's given to you. There are 3 questions given. You can download from CN. I already uploaded in CN. Please download from CN. I am taken 3 different types of elements. Number one is the rectangular. I think the width 100 and width is not matter now, but it is a rectangular section. Another one is an I section. Third one is on T section. All right. We will solve these questions today, but I have taken 2 sections of this. Number one, we go for step 1 analysis for its shear force and bending one, right? And then we do derivation for bending stress. Once you got the equation for bending stress, we'll go back to these questions to solve for bending stresses. It's good if I use the same question to find out the bending stresses, then you will appreciate what we are doing, how these calculations are done, or the analysis of beam is taken, right? Now let's start with, let's go through this beam. All of you can see, do you have the paper with you? It's good you download or you have a blank paper with you to solve together with me. That is how you have to practice, because the calculation you must practice. Can you all take the, if you can, please switch on your camera, take the paper and start solving. Am I audible to you? Am I audible to you?
Yes, please.
Okay. Can you all please take the paper, pen, and the calculator, work together with me. You can also correct me at times if there's any mistakes. Please help me, and then you also practice together with me. Start with, you are given with a cantilever beam. It's a cantilever beam at a portico, maybe a house or any type of construction, using 2 segmented rectangular section. The cross sections are varying, but they are a rectangular section. They have width, but the depths are different as shown in figures. Okay, same width but depths are different. Analyze the beam to determine its bending moment produced at D, the fixed end D. Let's calculate this. Since you said you still have not familiarized with these bending moment shear force, I start with calculating this part first and then go for stress, right? And then second question is on a wide flange I sections given with the different conditions of loading. Let's do one by one. I start with this. Is the condition of the support, loads, sections all clear to you? With that, I continue with the calculation part. With the support condition, fixed support condition, and a load at this point to be A at A, let it be PA is equal to 277 newtons. Very simple one, 277 newtons. And then its fixed support, let it this be B. Can you see the screen? All of you can see the screen?
No, no, no.
No.
No, please.
Not shared? One moment. If we start drawing the bending free body diagram, meanwhile, it's stuck. Hang on. One moment. Okay. How come I keep sharing? Oh, you can get it now, right? A. Is this audible? Please answer me. At A, let it be PA is equal to 277 newtons. Very simple one. 277 newtons. Is it audible?
Yes, miss.
Okay. And then it's fixed support. Let it this be B, no D, right? Undo. There is a B is found here. You have a B at the midpoint, midpoint, and this is D, and these distances are equidistant. They are 4 and 4, I think. Is 4 and 4. 1.2, 1.2 meter. 1.2 meter and 1.2 meter. Right. These are the given conditions for you. Other things you can ignore for a while until we finish first part of the analysis, which is your shear force and bending moment. Okay, now we're going to calculate shear force and bending moment and then plot it, right? I leave this space for drawing for the things. I do the calculation here. All right, you must be recalling your support conditions, and you should be knowing what's happening when it is a simply supported, when it's fixed, and when it is roller or hinge support, right? And due to this load, what will happen when you press here, when the load is acting at this point, automatically it will be distributed throughout the member, right? And also to the support, right? The support will tend to react to this load, isn't it? I repeat once again, whenever there's a loading, maybe at a point load or many point loads or a point load and some UDL, in all case, there will be a reaction created at this point. All the forces in y direction equal to 0. All the forces in x direction equal to 0. All the moments is equal to 0. Okay, you can follow all three dimensions for now x, y. So I write for x, y only. Okay, I can solve by these things. All right. In this case, let's take the first one. Right, I use the first one, which is sigma Fy is equal to 0. Shall we substitute one by one so that we can find out the unknown? B, and this one is B. All right, start from here. No, number A. Is there any force or reaction happening? Right, the forces or vectors always go with load and magnitude and direction sign. What is the direction, positive or negative? Okay, come to support D. What happens at support D? Is there any load or reaction or anything? We are only solving for forces in y direction, in this direction only, y direction only. Down, up and down, upward or downward. In that case, when I start from A, there is a downward, and nothing over A to D. At D, there is an upward, isn't it? A positive or negative? Positive. RD is equal to 0. D, okay. Now proceed with RD is equal to, hence I can write RD is equal to 277 newtons. Whatever applied, it is reacted by the member at D. That is our one answer. Is this clear? Let it be one answer. I will do the drawing later on. We do the drawing eventually. That is easier for you to understand. Come on, let's draw this diagram. Okay, I clear some space here. Fine. I'm going to draw. Take this as the axis, this is the axis. Okay, start from here 0. What is happening here? Is this 0? Shear force, load, force in vertical direction. We are solving in vertical direction only. There is no solving in y direction, I mean other direction, which is x, because there is no load, isn't it? Only up and down. Can you answer me? What is the load here? How much is the load here? Is there any load? 277, which is downward, which is negative. So I must go the drawing down. If it is positive, I go up by convention, sign convention. Since it's positive, I go down until 277, negative 277. So I mark this value, right? Then proceed to B. Is there any changes here? Because this force is being distributed, right? Proceed to B. Is there any load here? In between, if there is any load, you need to add or subtract according to the directions that is there. But there is nothing, okay? I can still continue. But let's see whether any load is here. There is no load. But there is one reaction at this point, isn't it? How much is the reaction? Point, when you, I mean, just assume to be this is continuing. There is no change here, no change here. I'm talking to the member according to the cross section. When I travel from here to here, I go from A at B, I have nothing, and then the same thing follows because there is no other load which can change this magnitude. Just keep moving. But at the support, when I reach here, I already having with 77. When I reach here, there is a negative here. I mark here. When I reach here, there is a positive. There is a positive 277. I need to add positive 277. I need to add. So I add positive 277. Then it will reach 0. Right? Then my drawing will be, shear force drawing will be like this. Is this clear? Put this value only. For your understanding, put all those. Right? This is how it is happening for shear force diagram. S of D. Any question here? Right. We move on to drawing the bending moment diagram. Say bending moment, it is a reactive or resistive moment offered by the member. Okay. Is there any restriction here? No, it can freely move, right? Means zero. Moment is equal to zero. You have to understand that way. A bit analogy is required in your thinking. I repeat, moment is not restricted A. It can freely move. So resistive moment or reactive moment by the member is zero. It cannot react to the load. Reactive moment at A will be zero. Start from A. Go to B. Is there any loading that is causing any differences to the structure? No. When you reach this point, there is a fixed support. This gentleman will cause a bending moment in this direction. Why I say like this? Because the loading is in this direction. It will tend to move in this direction. Due to this load, it will tend to bend in this or react in this direction, which is said to be MD. MD. That is the question asked for you. The moment is F into D, right? Force into distance, not only force. So when you talk about this point is zero. When you talk about this point, what will be this one? Force into direction means negative, right? Negative. This is positive. I write it for a while. So it will at B. There will be a moment at B, which is anti-clockwise. And when you go to D, there will be another moment at D, isn't it? Yes. BD. This is AB. Treat it as AB, easy for you. AB, and there will be another one BD, isn't it? BD, because of this one. And then there is another. Is there anything else? At D. At D, there is already a reactive moment due to fixed support. Positive or negative? Positive or negative? Already written there. Positive, correct? Once again, you have to go from one end to another, easy for you to understand. We are talking about the resistive moment offered by the member. I start with this point. At this point, it will be zero because it is there is no resistance offered by the member due to, if it is fixed, there is a moment. I cannot put zero here. Okay, so zero. Moving on to the member from A to B, there is a distance. Because of the distance, there will be a variation of the load distributed. Hence, it will automatically create a moment. I will explain what is moment further. When you go for stress analysis, you will really understand even better than what I'm doing now. What is moment, what is stress. But to calculation purpose, let us finish this one. Moment at this point will be due to this loading into distance. This loading into distance. It is downward, so I put negative right here. Moving on here, there is a portion also offered by this port, right? This port. So I repeat the same loading by this one, which is MD minus BD. What is it? Minus BD. If it is uniform, we can put it together. Because for your understanding, I just split and show you. Plus, when you reach here, at this point, it will be MD. Is this clear? Now substitute the value. MB will be, how much is this? 277, right? Same loading. 277 times 1.2 meter. Again, another value, which is 2.77 Newton times 1.2, same value. So you can even put it as one equation, but for understanding, I put it like this because it's going to vary after this. You need to have an answer. And then plus, what will be the value? MD, which is required, right? Which is the value we require. At the end, we will have MD is equal to, you repeat all this answer. What's the answer? Can you get me the answer, please? Moment diagram. Start from here. I put the axis, right? At this point, how much is the moment? Anybody? I'm doing bending moment diagram. This is the value for me, 334. Let it be like this. At this point, exactly at this point. I don't put the dotted line. Go to complicating. Minus 332.4, correct? Newtons, unit important. Proceed. So because of the distance again, there is a distance from load, 664.8 negative, right? Newton meter, Newton meter. Okay, but right, because of this loading and the reaction, there will be another line like this coming out. It will not stop here. There is a reactive moment caused by the Newton meter. Hence, I need to join here. Go back to zero. Not curvilinear, it's a straight line. I need to join here. Go to zero already. This is your bending moment diagram. Okay, this is how we draw it. If you want, I repeat once again. We start from here for this loading. Why I calculate separately to mark this value? Otherwise, you can do it together. I mean, after you do few questions, you will start doing yourself all these answers. From A, we draw the bending moment diagram. There is no resisting moment offered by the member, so it will be 0 at this point. So I mark 0 Newton meter here. Moving on, this load will cause the moment against the support only, above the support, right? But we can draw part by part because of the distance is growing. So from here, section by section, at this point, it's not a support, the section is changing. So at this point, we can mark, better to mark the value here because the section is changing. Otherwise, I can just leave it through one triangle only. Because the section is changing, I should know what is the moment here for my next calculation. That's why I'm marking here. So this moment will be this load into this distance. That is why 277 into 1.2 will be 332.4. That is the value I'm plotting here. Moving on, you will have same loading increasing because of the distance increasing. This load times this distance, isn't it? This load times the total distance, for your information, 2.4 meter, right? The remaining portion. So it will be added, or you can take it to be 1, or you can take it be added. This portion plus another portion, which will be another 2.4. And put together you will have double times 300, here 300, another 300. So you will reach this point 664.8 at this point because of this distance and the loading. That is one calculation. If this is due to the loading, right, the number 1, but there is another resistive moment offered by the support which has to be added, which is positive in direction. When you add it, automatically your drawing will drop down. Initially it was at this point negative, right? All this, if you take this as axis, going down is negative, going up is positive. Already it was in negative minus 30, minus 66, 664.8. At 664.8, it will go back to 0. So this is how you do the bending moment diagram. Okay, all negative here because of the resultant direction of loading and moment. Any question? I stop here for bending moment. Next portion, the same question I will continue for your calculation of shear stress. Any question here? Do you have a question for the number 1? Shall we move on to second question? Hello guys. No question. Okay, let's move on to next question. Can you start doing the next question? Which is this one, I think. This one. Can you all do it in a paper and put it in? Again, all of you copy down. If you're downloaded, you can take from the paper that you have. Otherwise, can you please solve this question? Start. Everyone, switch on your camera. Brian, Changjia, Chongzi, can you please switch on your camera and start solving the second question? Give me the answer. I give you 5 minutes time. Is that okay, or you need 10 minutes? Same procedure, draw with the free body diagram and then proceed for calculation of the reactions which can answer you for the unknowns. Applying the equilibrium equations, draw a sub-diagram and then bending moment diagram. Can you do it? All of you? Okay. Switch on your camera, please. I want to take snap. Switch on your camera and do it. The second question, which is displayed there, you just copy down a wide flanged eye section of standard size. Good, thank you, Jason. One by one, please switch on your camera and start doing it. Very simple, same procedure. You can check the answer. If not, I will work out, don't worry. Make an attempt. Practice makes you perfect. Only two people have switched on the camera. Can everyone switch on? Kairan, Khalif, Laoshu, Lamshu, Lazy, Limri, Limrong, Martin, Mitchell. Only 5 of you was on the camera. Thanks, Martin. One more minute.
Miss, do you finish marking the task 1 paper?
Sorry, I need another 1 week time. Shall I give you this weekend?
Sure, take your time.
Sorry, I planned last week. There were at our conference. They actually canceled the conference. Suddenly they changed the time. I put exactly at your class time last, so I couldn't complete it. This week, sure, I will give you. Okay, let's start. Okay, time up already. You can check the answer now. Come on. Calculate bending moment at support D, MD. Question is MD, similar to the one, but there is no free, but one moment is added. That's all. Slightly changing the moment diagram. Okay. Solution, solution for 2. As usual, you need to know the sign convention for moment and reactions, right? You do yourself. Or I just quickly write down. We follow the sign convention, two-dimension analysis. This is positive, this is negative. Downward is negative, this is positive. This is positive, this is positive. And then another sign convention, clockwise and anti-clockwise. This is clockwise, this is anti-clockwise. Okay, clockwise, anti-clockwise. You hold the timepiece in left hand, and if you want to give the key, you will turn it like this, isn't it? So from your right to left, that is why positive. Left to right is negative. I keep all this convention in hand and then proceed with solutions. For solution, I start with the free body diagram. My free body diagram is one end is fixed, right, into the wall, and there is a. At A, there is a load. PA is equal to 22 kilonewtons, right? Newtons or kilonewton. Now the value is very high. You must be able to imagine how much is 22, right? 22 kilonewtons. Kilonewton. You must have an imagination power. How much is 1 Newton? Quickly. 10 kg, right? 10 kg is 1 Newton. 10 kg, you can imagine your rice bag. Take rice bag 10 kg, you can understand the weight of the 10 kg. Now, where we are? It's not moving. Okay, now you can have another moment is there at what distance? The distance matter, 1 meter, 1 meter, equidistance as well. Easy for us to understand. This is B. Okay, at distance, what is the distance? 1 meter, 1 meter. This distance is 1 meter, and this is also 1 meter, and the support is at D, and you are asked to find out what is the value of D with this loading and moment conditions of this member. Okay, there is a moment anti-clockwise or clockwise with the support condition, fixed support condition, and a load at this point to be A at A, let it be PA is equal to 277 newton. Sorry, hand, and then proceed with solutions. For solution, support is at D, and you are asked to find out what is the value of D with this loading and moment conditions of this member. Okay, one moment. Is it audible? One moment. Let me check once again. Okay, now the second question solution. Condition and a load at this point to be A at A, let it be PA is equal to 0 D, and I take for x equal to 0. This is the time. Kilonewton. Now the value is very high. You must be able to imagine how much is 22, right? This is also 1 meter, and the support is at D, and you are asked to find out what is the value of D with this loading and moment conditions of this member. Okay, there is a moment anti-clockwise or clockwise remains the same because there is no loading changing here. So I just put it assume. Hi guys, there is one correction here. This is positive, right? At the end, there is a downward load which is 22, which is negative, and then it is reacted, right, counteracted by the reaction RD, which is upward positive. Please change this, make this correction. This is positive. Okay. At this point also there is no load, but moment is there. Just keep it as it is. This point, and keep it as it is. This point, keep it as it is, and then moving on. Any loading here? No loading here. Supposed to be not changing, but when you reach here, if I remind this one until this point, I reach minus 22. When I reach here, there is a positive one, right? So when you add this positive one, it will get closed back to 0. That's how you will be having RD is equal to positive 22 newtons reactive force for the load at this point. So your shear force diagram will be something like this. I repeat once again, we are doing only force in the y direction. The y direction application of force is like this. When you plot it from axis 0, minus 22 because negative, so going down, and then moving on, it remains the same because there is no loading onto the member in the y direction. I follow like this until this point, but at this point, this point D, what? Yeah, what? Okay, at this point, what is this one? D. At this point D, but I write D clearly. D, but it's reaching 0. I'm just showing reaching 0. When you add with this one, you finish. Then you left with the visible value is RD, which is the reaction that you need to know for your analysis purpose. Okay. Any question in the shear force diagram? If not, we go to, this is your shear force diagram. If not, we go to bending moment diagram. We did shear force diagram, or value of shear force is known. Now going for bending moment diagram. I'll do it once again, no problem. Come on, answer me for the bending moment. Let me calculate, do the calculation here. Then drawing I can take some other place. Come on, start with A. What happens at A? We use the equilibrium equation, which is our good old equation. Sigma md is equal, m is equal, not md. All moments, all moments is equal to 0. Okay, all moments are resolving moments at the support. I take it as like this. Easy for you to clear. All moments, I resolve all the moments due to all the loading to D equal to 0. What is this value? Over here, you are resolving until this point. Either put it as 22 over by 2 or 22 times 1, another 22 times 1. Okay, it's a point load. Right. And then do the load at this point. Okay. Now, which will be negative 22 times, also same, right? 2 times 1. We need to add at point. Positive or negative? Also negative, isn't it? Let's solve this one equal to 0. That is done. Now moving on, we can calculate the value. Resolve and tell me what is the value D. I did all the moments here equated to 0 or towards the unknown, which is sigma md equal to 0. Right. Let's draw the bending moment diagram. Here. Let's start from here. 0, right? 0. Listen carefully. I put the axis here for bending moment diagram. Start with, at this point, is there any bending moment? Some value which is 22, right? 22 point is negative, right? I put here, I just draw somewhere here 22, reaching here is about this point due to this load into distance. About this point, I will have some value of 22 newtons, negative. I will get, let it be like this. So I can here. Is there any change here? There is a change, right? Due to this low moment. How much is this? 34, right? So I need to go down positive, add positive 34. You will end up with, answer me please. When you add positive 34, what will be the remaining? From here, add 1, 2, 3, 4, 5, 6, 7, 8, 34. You add. You end up with at this point. Am I correct? Are you following, everybody? 12 kilonewton meter. Because I'm adding, right? There's a positive. So it's already negative. When you add positive, become higher to lower, you subtract, put the sign of the higher value, which is positive. This is positive. That's why you go up, crosses the axis. Then what will happen? Proceed to here, proceed from here. It will remain the same because there is no change here. But that is a moment at this point, isn't it? It will lead to moment at this point. What's happening here? How much is the moment here? 10. So you will reach at negative 10. So join these two, your job is done. Finish, bending moment diagram, finish. Negative 10. Is the point clear? You can use the same method. If you cannot understand, you need to study, repeat and repeat. If not, you just call me or text me for appointment. I will repeat once again for you. Okay. This is okay. Any question in the second? We will solve for shear force and bending moment, and the values are also obtained. Okay. If any question, you can stop me. Otherwise, I'll continue with the next topic on. This is a preliminary calculations for shear force and bending moment. Next, we have to move on to the same question will be used for calculating the stresses on the same member. Before going for this, let's do the derivation for bending stress. Have you copied? I will give you the final with solution. I will post on tutorial. Okay. If you have solved, you can correct it now using this. Otherwise, I will post it. Wait for my posting in CN. Okay. Is there any question? Automatically. Okay. Let me share the screen for you. Remember, last class I introduced bending stress theory, right? Whenever there is a couple, the stress can be caused by a couple or the loading due to the axial. Last time, so far we are solving for axial loading, and this one is the Perpendicular. The load acts when the load is acting perpendicular or across the cross section. You will have to analyze for the bending stress. This is what I'm going to do now. Let me open this derivation. It's a simple derivation, will be very helpful for solving any new type of problem that you will encounter in your job place or in any future structural design you're going to do in your capstone or in your FYP. That's why it's be very helpful. This derivation, follow how they have taken an elemental area to analyze, come out with the equation for finding unknown. It has so many parameters to calculate. You will see how it is done. Come on. I take this one, right? Let's take this member of so and so length, right? Length and then the depth, okay? Just showing the cross section of a member, cut section of the member. Once you apply a load, right? Once you apply a load or any type of moment at the ends, it will tend to bend like this. All right, there is two different position. This position is like this and this position turned to like this position changed to this position, right? There is a compression here, right? Compression means contracted. The members are contracted at this point and this one elongated or extended, right? Extended, right? Originally it was L, now changed to another dimension. We'll see what is happening here by a diagram, right? How to calculate? See, there is a deformation due to a loading, right? Imagine there is a load or moment is acting on it. That has caused the original position from here to another position like this. Let's analyze this member by giving all the parameters and the related formulas. Let's derive the equation. When I take the member separately, when I just take the cross section of the member at any point, then it will look like this. A smaller dimension will be something like this. Originally it was like this, isn't it? Changed to like this, correct? Originally here position was like okay. Originally the cross section was square like this. The member was square like this and then changed to like this because this is contracted, this is extended. Top position was contracted, the bottom portion was extended, right? Just relate this to because it's a curvature, right? It is not a linear or just a displacement. It's a curvilinear, right? Hence, by using curvilinear formula, you are able to derive the equation for the same. Let's do that derivation. I just complete this circle. Right? And then I take this to this one. There's another one you need to know, the central position. Just draw it like this. You can all see, right? A bit bigger so that it is easy for you. Okay. So if you take this position, this is a neutral axis, right? Say XX, neutral axis. After elongation, it will be, this is the neutral axis and there is if you compare this distance, it will be changing to the new element will be somewhere here, isn't it? The new element will be somewhere here. Let this be Y, the change in her length. Let the change in length be Y. Then you will know what is the value of. See, this deformation we cannot measure directly because it is not linear. It's a curvilinear. By following curvilinear equations, we will find out, or by the formula for finding R, finding length, arc length, finding angle, right? Using that method, we can easily find out how much is the value of this bending stress. AB, second section B, CD. Okay, there is shifted one as the CD. Mark this as C and D. So the distance between them will be Y. Okay, let's mark like this first of all. Moment, direction of moment also we can mark here like this and then like this. Okay, direction of moment. The moment couple I'm drawing, and then you have the center. Mark the center. Going to center as 0, and then make the angle as I use the same value. I mark the angle as theta itself. Theta or phi, you can use it. Let's mark this as theta. And then what are the other dimension need? Let us mark this radius as r. Okay, radius as r itself. And then what is this? Another layer, right? This is AB, and I have CD because of the extension. Or take any axis. Say for example, I use other color, black. I just use the red. Reference axis like this, and let it be CD, and let this be Y. Okay, the value be Y. Okay, these are all the assumptions that we are making. I repeat once again, we have taken a beam of length L and say length L, and then applied by the moment, N moments. Because of the moments, it will have bending like this, and the deformed position is shown here. Once this is deformed, then conditions are taken like this. Neutral axis is marked as AB. A distance or any layer, choose any one layer at a distance y, below or above you can take, right? Both are deformed section, right? Here also deformed, here also deformed, above also deformed, bottom also deformed. Let's choose CD as a section below AB or below neutral axis at distance y. Okay, with that you will know how much is the deformation. You really have to imagine, and when I say deformation, it's in the circular direction, right? You have to imagine the original and or find out the difference between original and the new position, right? In this condition, we can calculate how much is the deformation and the angle and so on. So what is the angle of, when I say R is the radius, and then the angle is a theta, include angle as a theta. What will be the arc length AB? Can you calculate what is the arc length AB? Anybody? Arc length AB. This is exactly the neutral axis is given as AB, and the layer I have chosen as CD. Come on, can you give me CD? Similarly, can you give me for CD? Arc length is given by CD. Arc is given by the radius times or distance. Radial distance times the included angle. I use the same included angle because of also having an included angle of theta. What would be the value of OC or OD? Anybody? Please see the diagram carefully. Answer me. What would be the distance OC or OD? Come on. Draw if you want separate one for you. Our diagram is like this. My angle is this one, CD and CD. This is O, also making an angle theta. And my distance is somewhere here is given as R. Right? And from there is Y. And how do you define strain value? Strain is equal to, answer me la, strain is equal to, we are trying to find the deformation, right? Strain is equal to change in length by original length. Original length. What is the time now? We have time. We have to finish this. Right. What is the change in length here? Or original length? The change in length we already found out, right? The change in length is found out already. What is the change in length? Anybody? Change in length for AB? Change in length will be CD minus CB, right? Originally it was AB, neutral axis, but changed to CD, isn't it? C and D. Am I correct? The change in length is given by CD minus, very simple one if you think and answer my question. So strain is change in length is CD minus AB, correct? Original length will be AB itself, right? So the change in length, the extended value at a section CD is CD, value of CD, which is CD minus AB. The change in length to the original length can give me the deformed section to the original section can give me the change in length or delta, correct? Okay. How much is this one? Let's calculate this from here. CD minus AB, which is R plus Y times theta minus R theta divided by my AB is equal to R theta. If you simplify, you will end up with, if you simplify, If you simplify, you will end up with the value for strain. Value for strain is given by, can you simplify, r theta minus plus y theta minus r theta divided by r theta. So it will be cancel y theta divided by r theta, again cancel, you end up with y divided by r. Correct? Shall we arrive at strain value? Right? Shall we arrive at strain value? It's better I show the video again, or I hope you can imagine the pipe like this was bent and it has reached a change in position like this. I want to know how much is this deviation, how much is this extension, and how much is this contraction in an average, right? As an average. That is found by finding a strain value. Hence we found the strain value by following the formula for strain, which is change in length to origin length. Origin length was AB, right? Origin length was AB like this. The change in section we have chosen as CD, right? Let's find out the bending stress. What is the formula for bending stress and strain? We got stress. Can we relate by modulus of elasticity? Remember, what is modulus of elasticity value? Modulus of elasticity, anybody? Modulus of elasticity is given by stress over strain, or ratio between stress over strain is given by a number. This is after given, the name is given after the scientist Young's modulus, right? It can be Young's modulus of elasticity or modulus of elasticity. It's a number. It means it's the value that is defining stress over strain. Stress over strain, or E is equal to stress over stress. I denote by this one. Strain I denote by this one. Can we now find out the stress? That is our requirement, right? The bending stress sigma can be found by E times strain. How much is our strain? Y over R. Can we now substitute conveniently? Y over R. So thus we found the value of bending stress. Originally the neutral axis is, say, L value, 10 meter. Once the moment is applied, change to 12 meter, right? The bottom layer, you choose any distance from the central axis. The bottom layer keep increasing, say 12 meter. Because this number I can find clearly how much is the variation. But in this case, it's a curvilinear, right? It's bent like this. I cannot notify how much is the deformation. By using mathematical equation only, we can find how much is the value. That's why we have to derive the mathematical equation. We found the strain value, we found the stress value. Next, let's find out the equation, bending or flexural equation. Right. Let's recall another set of formula. Okay, when I cut section at this point XX, I will have the cross section like this. Okay, let me do this one. I draw the diagram here. Cross section will be like this because it's a square section. Let us take this to be a cross square section, right? This is the neutral axis. This is the central line or central axis or neutral axis. Say I keep the same name AB, right? And then if you look into the stress distribution like this. Above the neutral axis, it will be like this. All values are like this. All values are like this. And below the neutral axis, it will be away from the member. It will be away, acting outward. So there is a two different direction of stresses acting in the element, above and below. One can notify two type of stresses. That's why you have hogging type, which is compression on top and tension at the bottom. Put together, we can say this is acted upon by a moment called M. Okay, net result or overall result. Right, you know that the member is subjected to the compression here and tension here. That's what I'm plotting here. On top member, right, above the neutral axis, the member was subjected to inward stress. Below the neutral axis, the member was subject to outward stress. Overall, we can say it is subjected to a moment M. Okay, right. Let's find out how much is the M value. How do you find out? M is equal to, you see here there is a variation between up and down. When you draw the diagram, okay, I do it here. When you draw the diagram from here to here, graphically if you represent, I put the line here. When you graphically represent this point, it is going inward, right? You will have a maximum value here, reducing, right? You will have a maximum value, reducing to 0 at this neutral axis. Moving on, it will be in the other direction, reaching a maximum at the outermost layer, okay? In this direction, and this is in this direction. Compression and tension. This is compression, this is tension. These are neutral axis. Okay. When you plot the distribution of the diagram, right, the stress distribution diagram, you will have like this. Top member will be subjected to compression, bottom will be subjected to tension. How to find out the net value? Because it is distributed between these limits. Okay. See the limits. High big value, right, positive value to a 0 to another negative value, right? The stress is negative at the bottom, at very high at the bottom. To calculate the overall value, the net value of the stress acting due to this moment, you can integrate by taking an elemental area. Okay, when you take an integrate over the limits or over this area, say if the area of the element is cross-section area of the element is A, integrate over the area and then multiply the value one by one. Just take the value one by one. If you take an elemental area dA, right? If you take an elemental area dA, say dA on the diagram, stress times y times dA. Okay, I write this statement first. Stress times y times dA, right? Bending moment. From this formula, you have this YR, right? YR. And then you have M value stated, Y times D times A. Okay, proceed with this. I can write what is our stress value. Substitute for stress value will be EYR. And then there is another Y, another DA. I just substitute the value of stress. Okay, you end up with E times R Y square dA. This way also you can define it. Okay, either way is okay. Just for understanding only. Right. Next, followed by. Please stop me if there is if it is not clear anywhere. I'm just substituting the value. We got it. So after this, I proceed with. I use the same notations. We end up with the value M is equal to, what is y square dA? Can we do you remember what is y square dA? Recall your statics, moment of inertia, right? Or square of second moment of area. We can call this as second moment of area, or right here. So this name is called second moment of area. Moment of area, because this is a second moment of area or moment of inertia, in simple word. Okay, inertia, right? Y square dA. Y dA is the cross-sectional area of a member that was deformed to Y, and the area is dA. We can integrate and say, but if you square it again, that area, you will have Y square dA, or second moment of area. The technical term used for second moment of area is called moment of inertia. Let me move on to this one. Okay, I substitute the value of Y square dA as I. Right, the good old notation that we are using is a I. Is it clear? I end up with EIR. Alright, can we now substitute for stress value? We got one moment value. Wait, I separate this one. This can be, what is ER? Just for convenient purpose, What is here? Sigma over y. Am I correct? Sigma over y. So I just substitute this value. Substitute for E r equal to sigma over y. I will have the equation m is equal to sigma over y, and then I. Am I right? Please correct me if I'm wrong. We got another equation in terms of I, right? I and stress. This is what we wanted, right? Bending stress. So I got one equation, I got two equations. Just we can assemble all of them together. I wrote in terms of modulus of elasticity, another one in terms of shear stress. So we end up with shear stress is equal to my over I. That is our ultimate value that we have to determine. This is our ultimate value, bending stress, right? Bending stress. Right. From there I can get another equation for you. If y is one moment. What is y here? What is y here? This is AB, right? This is AB. I took a distance of y at CD in the member. When I reach the extent, the complete extent of the member, right? This is the last fiber, end of the fiber, like this one. Earlier we took some distance, right? Earlier we took some distance from the neutral axis, say y. If you reach until this one, it will be y max, okay? It will be y max. For finding y max, just substitute the value, replace y as y max. You will find, right, y as, when you reach until this point, let it be y max. Then you will have the value of maximum stress is equal to m y max divided by I. So this is also ultimate stress that one can derive using this formula, bending formula or Flexural formula. I'm going to introduce another one value for you. What is I max by y? I by y max. This gentleman. What is this I by y max? Can we replace this one? I by y max, another equation. I by y max is equal to, you can just name this as sectional modulus, okay? This is referring to sectional modulus or S, just simply S, sectional modulus. You can replace the sectional modulus. Sometimes in the equation or in the question it is asked to find sectional modulus. In that case, you treat this ratio as a sectional modulus. You can conveniently find if your sigma's value is there, right? If you are given a sigma value and asked to find the sectional modulus, you can use this formula. M times M over S, right? M over S. Okay, this is another equation we are reaching, I think fourth equation. We found strain, this is 3, this is 3, this is 4. So we got another equation called sigma in terms of sectional modulus. Sectional modulus. We can also write the equation in terms of sectional modulus. Okay, any question so far? And this sectional modulus will vary from I section to I section and then T section and so on. Can we now draw the diagram? Let's draw the diagram. Distribution diagram, stress distribution diagram. Okay, number 1, I section. Let's draw the value of I section. If the member, beam member, like this is the beam, okay? If this is the beam, cut section, say YY. The section YY will have, please imagine, I cannot do the animation here. When you cut, the cut section will show an I section. The cut section can be a T, I, L, right? It can be T, it can be I, it can be L of any type, or just simple rectangle, any type, any cross section it might be, okay? Now, if you take the cross section of I, the distribution of stresses will be like this. I'll show the value here. Starting from, if you draw the distribution of the compression and tension, compression going inward, just put it like this. Is be reducing towards the neutral axis or not? Neutral axis, AB. Will it be reducing to neutral axis or increasing towards neutral axis? Compression. Increasing or reducing? It will be reducing to 0 or the neutral axis. And then what about the loading is here, right? The loading is happening here. So what will happen to the flange below the neutral axis? What will be, is it a compression or nothing happen or tension will happen? It can be a tension member, right? Extended, the member will get extended, elongated, something like this. So this portion is tension, this portion is compression. For the T section, I draw the T section here. Let me finish with the T section. Okay, how will it be? Neutral axis, say neutral axis falling here, right? Neutral axis. From the neutral axis I draw. The top flange will be having maximum. Towards the neutral axis will be 0, isn't it? Subjected to 0. What will happen to the bottom portion? You can do this way or this way also fine. But provided you show different direction, that's important. So it will be a compression type, right? Reducing in the cross section. And the bottom it will be tension going, because it's away from, after the neutral axis is totally further from the loading. That too, the subject member is a slender member, right? The material to under which, or material which is subjected to this loading will be smaller compared to this one. That's why you will have this portion is maximum. This will be a little one. Okay, subject to tension, this will be subjected to compression. Okay, I stop here. Any question you can ask. Okay. Do you understand the derivation? Okay. We got a statement relating to the Flexural formula with 3-4 phrases. According to the data given, you can calculate the unknowns. Right, let's do the calculation. Continue with our calculation. Any question you can ask me meanwhile. I share the screen. Let's go back to the calculation that we did, and then we can calculate the stresses. One moment, I'll share the screen. This is the calculation. Today I have given you 3 questions in the CN tutorial. We solve for moments, right? Number 1 question, we solve this one. Just now we solve for shear force bending moment, right? Now let's add with the component, another component of calculating the stresses. What is it? The question is extended like this. If width of beam is 50 centimeter throughout, determine the maximum bending stress in the beam. See, the width perpendicular to the section is given. Last time it was not given, only depth was given. This time the width perpendicular to the section is given to you. Come on. When you do this, why the width is given? Because you need a section, right? The section is undergoing the stress. Only through the cross section you can see the stress distribution. That's why you need a cross-sectional area when you do these type of bending stresses. Come on. Start with, you already know these moments, right, at different points, and then the main thing that you have to calculate is sectional modulus. Sectional modulus will vary from different section. There are steel grades suggested by ASC, right, the American codes, British codes, Malaysian codes also there, but we follow American codes. All the calculations are based on American codes. I will send you the pages from American codes for you to know. You can also find the same codes in your textbook. Okay, I have circulated the textbook, right? Please go through that. Strength of material by Pierre, right? You can follow that textbook. You can find these tables at the end of the pages, all through the appendix you may have. According to the section, according to the material, the value will be vary. But in exam, if it is asked, we will provide the formula for now, but not every time. Better to remember at least for common sections like rectangle, square, circular, right? For rectangular, the sectional modulus is defined like this: bh square by 6. So accordingly, if you substitute the formula, b is width is 50, right? 50 centimeters given. So you can change to meter, and then by h depth, number one depth is 100. So I just split and explain so that easy for you. Right. So if you can calculate the sectional modulus number 1, you can arrive at the make use of the equation related to sectional modulus. You can find the answer already. So the depth is 100. I have substituted the depth 100 divided by 1000 will be 0.1 meter, and then square divided by 6, you get the answer already. And then similarly you calculate for BD, same value. Width is same all through. Width is realized perpendicular to the paper, and then 0.15 is the depth of this member. With that, I have found the sectional modulus for the second member also. Knowing all the sectional modulus of the members, you can go for make use of this Flexural equation just now we derived in terms of sectional modulus, moment. You may have to find out the correct phrase, correct equation that can relate to your data given. Now you are given with moment and shape moment, and then section also can be found by using the cross-section dimensions given to you. Hence I use this equation to find the stress for AB number 1. Accordingly I got the answer. I got the answer like this: minus, see I have substituted the value for AB, then top is moment. The corresponding moment at AB and the section modulus are substituted to find stress value in AB, followed by BD. Substitute the corresponding values of moment which you determined before in the beginning. I explained already in the video, followed by section modulus just now you found, and then get the answer for maximum shear, the stress, maximum stress in BD, which is minus 354.56. So this is how your questions, normal questions which you have been solving so far, can be extended to calculation of stress by introducing the equation, direct substitution only, right? And this is a big phrase. I will write it overall when we are going to solve for big questions. Let me solve the second also, then go for one exam, past exam question, right? Or you want to solve this question? You want to try this question for, well, let me read the question for you. Last time, very first was the rectangle. Second one was the I section. Now we are going to solve for T section. It's interesting how the profile is keep changing, right? Where the maximum, where the minimum, and which profile is significant in your design. This is how the engineers will design. When you go to side the reinforcement, after the shear reinforcement, shear bars, everything is considered based on this type of analysis. Come on, anyone read quickly? 5 more minutes. I don't know now. Limri, please. Limri thing, please read for me. Read loud. Determine. Someone determine other. Are you there? Maybe Limrong? Can you hear me? Can you hear me?
Yes, Miss.
Please read for me.
Okay. Determine the maximum tensile and compressive stress, the radius of curvatures for the structural component given in the figure below. The moment of inertia of a T section is 100,
800.
60,
850.
has its central distance at 38 millimeter for its bottom flange. The cast iron T section forms part of a structure and is acted upon by a three couple tag one
Kilonewton. Kilonewton.
kilonewton meter couple tag one one
See,
hundred
Young's
sixty
modulus.
five
Young's modulus. Huh? Young's modulus. Young's modulus.
and neglect the effect of relax.
Yeah. Young's modulus 165 gigapascal. See, giga means how many? Anybody? Million means 10 power 6, right? Giga means 10 power 9. Okay, right. Come on, let's solve this one. Cross section is given. In this case, I see people are simply calculating. Even though I give numbers, they are simply calculating. Don't do the blind job. You are given with all the sectional properties. It's very simple question, two-line question only. You don't have to bother. If you start writing the given data, you have the section modulus, you have the what do you call the Young's modulus, and then the couples are given. See, the whole section itself is given, right? Even the y bar, I think y bar is also given. Wait, let me see. What does it mean? What can you read this sentence from here to here? Come on, quickly. The students make mistake blindly, you know. That's why I keep asking you to read. What? Please read for me this line. What does it mean? They simply calculate, although it is given. Come on.
Determine the maximum tensile and
No, no,
compressive
the
stress.
highlighted one. What highlighted one?
Oh, the moment of inertia of a T section is 868 times 10 to power negative 9 meter power 4 has its centroid distance at 38 millimeters from its bottom flank.
Okay, stop. Thank you. See here, it is clearly written as the centroidal distance. Centroidal distance means what? And that too, it is given from what is given. Centroidal distance from the bottom flange is given already. That means what? Your y bar is given already, right? This is your section, right? This is width of the top flange, width of the bottom flange, depth of the top flange, depth, right? These are the common section. And there is one point which is called centroid of the section you would have determined in statics. That determines the net force or resultant force acting or due to the force acting on the body including the self weight, right? That point is called C. That point may be located somewhere here, right? Somewhere here. This point is given to you already, and this point distance from the bottom flange is given to you already, right? This point from the bottom flange is given to you already, that is 38. The number is given as 38 already. Don't again calculate by following the procedure to calculate for y bar. Y bar is given to you already. This is y bar already, right? So just substitute in the equation for Flexural formula. You can easily find out the value for bending stress. Okay, I'll continue in the next class. I stop here.